Hi, welcome once again, wherever you're watching us from, from Africa, Europe, Asia, Eastern Europe, or Australia. It's GoGate once again, and we want to take every one of us through the structural design of a crane girder. Structural design of a crane girder in compliance with BS 2563. Structural design of a crane girder in compliance with BS 2563. In addition to structural requirements of BS 5950. It's GoGate once again, the institute that provides you with very enhanced technical information on structural engineering. We teach you manual analysis of reinforced concrete, steel structures, timber structures, onshore structures, design of connections, installation design by loadout, by rigging, transportation analysis and design of transportation support tie down lashing, design of transportation sea fasteners that can be cut off at site installation locations, design of foundation geotechnical structures, tank farm, tank storage facilities, crude storage facilities, heavy fuel oils, HFO, and everything that has to do with civil and structural engineering. Today, we want to concern ourselves with the design of a crane girder. We're going to take you through a live project. This drawing was sent to us from Saudi Arabia, STAAD.PRO, name of the company, STAAD.PRO. They sent us a lot of drawings. So what they are saying is they have an existing structure, an existing shelter. The shelter is about 1, 2, 3, 4, 5, 6, 7, 8, 9. About 54 meters, the overall length of the shelter. They have an existing crane on the shelter, an existing 8-ton crane on the shelter, and they intend to install another crane on the shelter. So they want us to carry out a structural integrity assessment of the shelter, in addition to its foundation too, that has been constructed, to see if the structure has the right integrity and the right strength as is to carry the new 8-ton crane to be installed on the structure. So we want to just teach us very quickly the requirements in the structural design of a crane girder. The first thing you want to do, so the company we said is STAAD.PRO in Saudi Arabia. The first thing you need to request for if you want to design a crane girder, okay, on a portal frame, is request for the crane data sheet from the vendor. So the vendor is supposed to provide you with the crane data sheet. This is the crane drawing in addition to certain technical information for the crane. In this case, we are to design an electrically overhead crane, and we have manually operated cranes, we have electrically overhead cranes. In this case, we are to design an electrical overhead crane. The requirement is to be as 2573, and then for the foundation reinforced concrete structures is to be as 8110. So it's an 8-ton crane. Information you'll be requiring from the crane is the minimum hook approach, the end carriage wheel center, the weight of crab, the weight of crane bridge. These are the information you'll be requesting for in the structural design of the crane girder. Okay. The first thing to do is to model the entire structure. Before we do that, I need to specify clearly that this location is in Saudi, and they have very high temperature, very extreme high humidity and high temperature. So the kind of insulation required, if you look at the roof structure, you have very heavy insulation. You need to cater for that when you're doing your roof loading. Because for Saudi, the insulation there is so as to prevent intense extreme radiation on the structure that can result to temperature stresses. So we do our load calculation for the portal frame. Firstly, you have dead weights. So, but before you do this, you would have to develop the structural model. So this is the structural model for the shelter. So we have developed structural model. If you look at it, if you look carefully, it's a shelter that has reinforced concrete and steel. So we had to do the design of both of them together instead. So if you look here, they said they have an existing crane operating somewhere, possibly between this bay and that bay. They have equipment that require the continuous use of the crane, and now they want to install another crane on the shelter. So the first thing is to build up the structure. That's the location of the crane. So this is the existing crane girder. They want to be sure that this existing crane girder can carry the new loads coming as a result of the 8-ton crane. Okay, so we build up the structural model, clearly ensuring that the elastic properties, member orientation, lengths are modeled correctly. Isotropic and prismatic characteristics of the structure is clearly and correctly simulated in your model. So each bay is about 6 span. So this is a single story multiple bay structure. Each bay is about 6 span. The foundation has tie beams from the drawings they gave to us. So we model it correctly in accordance with the drawing that they supplied to us. So this is the drawing they gave to us. So you see you have some foundations there, and then you have grid beams at those locations, So you have these 3 stanchions here. This is where this is the front elevation, and that's the rear elevation. Okay, so you could see this located where it's supposed to be, and at the rear you have those 3. So you need to develop your loadings. What are the loadings you would be looking at? For the roof structure, you have the weight of the pole lines, you have the roofing sheets, you have the insulation board. You have to get this information from the corresponding BS code, as you see there. You have fixtures on the roof. You need to get that. Total dead load is to be obtained correctly. You should know that total dead load is measured. The dead load on the roofing structure is measured normal to the inclination of the rafter. So you need to resolve that normal on plan. Okay, based on the slope of the rafter. In this case, it's 7.69 degrees, and then we get the total dead load. Then the portal frames are spanned as shown. So based on the spacing, the dead loads are applied onto the rafters. Then you obtain the life load where only access for roofing maintenance is permitted. The code provides the requirement for the life load. Then wind load for the location is in Conasinia in Saudi Arabia. The distance to the sea is between 10 and 100 kilometers. We calculate the wind loading based on the standard method of BS 6399 part 2, and they gave us the basic wind speed, mean hourly wind speed, and then we did our calculation to get the effective wind speed, which is the gust, and then the net pressure coefficient expressions, and we use that to calculate the wind load in at 0 degrees, which is transverse to the structure, and then we calculated the wind load at 90 degree longitudinal to the structure. In the transverse direction, we calculated the net pressure coefficient and used that to calculate the wind loads on the stanchions, and again on the wind load on the gantry girder, because when you have wind pressures in this direction, it affects the stanchions, the eave beams, and then the gantry girder. So we calculated that correctly based on the pressure coefficient. You can see the pressure coefficients as they are. You see that here you have larger pressure coefficient. You have significant wind pressure coefficients at A and B, and then at EF. So if you look at the external pressure coefficients, you see they are very significant at A and B. That's why you'll be having tie braces at these locations. At C it's quite small. C and G is quite small, when you have wind affecting this direction. So we calculated the wind loads and in the 0 degrees, and then wind loads in 90 degrees. Then the next thing is to calculate the crane load. So how do you calculate the crane loads? One, you look for, you obtain starting information from the crane, and what you need now is the weight of crab plus the crane capacity. Use that to calculate the reactions at the left and the right of the crane bridge. As soon as you get the crane reactions, which is F1 and F2, which are the wheel loads. The wheel loads, the wheels are, so for mildly tonnage cranes, the wheel loads are concentric, or they are concentric, like I said, they are equidistant from the center of the wheels. Okay, let me show you what I'm talking about. If you look at, okay, this is a crane data sheet for the crane good. This is, if you look carefully, supply power. So the span of the crane bridge is 10.05 meters. 10.05. That's to say the total span, which is 10.2, minus the minimum hook approach. Okay, minus the minimum hook approach. So you see the total span is 10.05 meters. Okay, so here to here, that's span of the crane bridge, 10.05 meters. Minimum hook approach is 0.401. Okay, now this is the crane, this is the plan view A. View A, this is the trolley. Okay, this is view A, this is the trolley. Okay, what you'll be looking for now is the crane bridge and the crane wheels. You need to get the span between the crane wheels, because the crane is a moving load. So if you look clearly here, you see the span between the crane wheels is 1.6 meters. And because the crane bridge is centralized, okay, between the crane wheels, the wheel load from the crane girder will be uniform. But let me show you a different design I did some time ago. If you look at, for heavy cranes, let's get this is a 20-ton crane. This is a very massive crane. That's a 20-ton crane girder. This is a 20-ton gantry crane rather. If you look at this 20-ton gantry crane, you would see very carefully in this instance that the crane bridge, if you look at the distance between the crane, so the span between the crane rails, the crane wheels is 4 meters, but the loading is such that it is not, the location of the crane bridge with respect to the crane wheels is such that the hook load is not centralized. So when you calculate the hook reaction, you would still have to determine the reactions from each of the wheels. This is usually this happens where you have very heavy have very heavy crane tonnage. Okay, so the distance between the hook points and the crane wheels in this instance, varies between 2.35 and then alternates between 2.35 and 2.19, as against what we have in the current design which we are looking at. So when you're doing this analysis, you get the span between crane wheels, you determine the reactions from the crane bridge. Okay, when you get the reaction F1, you increase it by 25%. This is a code requirement. Electrical overhead crane, you need to increase that because of impact. When it is lifting a structure, when it is rigging, there is suddenly applied imposed load, which is called impact. So that's shock, that dynamic effect as a result of the suddenly applied rigging. You cater for that on the structure by increasing the static load by 25 to give you this. The minimum static wheel load, which is the wheel load on this other side, you calculate the reactions, that gives you that. You also increase that for electrical overhead cranes. It gives that. Then horizontal loads, every crane during rigging, it swings a bit, and then so it subjects the crane girder to horizontal load. The code specifies that horizontal load that transferred through surge must be given as 10% of the weight of crab, which is the trolley, plus the crane capacity. So 10% of the trolley weight plus the crane capacity. Then how do you arrange your wheel loads? Crane girders are moving loads, so these are gantry cranes. So gantry cranes subject a girder to moving loads, and moving loads imply that the location of maximum moment would be changing as the point load changes along the beam span. So you need to get what you call the influence line. Influence line can be defined as the variation of a structural quantity, which may be shear force, could be bending moment, could be axial force, at a point as a result of moving loads. It is defined, influence line is defined as the variation of a structural entity or quantity at a point as a result of moving loads. So influence line can be linearized, it can also be quadratic, depending on the loads. So it has been shown that when you have wheel loads moving on a structure, just like when you design a bridge, we also use this in bridge design, the influence line that causes maximum moment, the maximum moment of the bridge, will occur when the wheels are arranged in this form. So you must arrange the wheel loads on the beam that will cause maximum moment. The code makes that provision. In addition to that, you also arrange the loading on the beam that will cause maximum horizontal moment, and then you arrange the loadings on the beam that will cause maximum shear force. Okay, so once you do this, you come to your design, develop your structure correctly, ensure that there are no errors, check your structure, make sure no errors, you're fine. Go to your loading, self-weight of the structure, you apply the entire structure self-weight, you apply the insulation, you apply the imposed load. The wind loads are calculated, you apply them in the X direction. For the roof, the wind loads they cause uplift, okay, on the roof structure, so it creates uplift effects on the roof. And then on the stanchions, you have them as lateral loads. So you apply wind load in the X direction, you apply in the negative X direction, and in the Z and negative Z in 4 orthogonal directions. That's the code requirement. Then your crane load. So this is the crane load. Look at how we applied that. So you apply that in the most critical point on the entire structure that will create the worst case. That this span is a 60-meter span, so you apply it equidistant between the center or the centroid of the entire structure. Okay, equidistant between at the location where you have the center of gravity entire structure, where will cause the most significant effects on the structure. So how have we applied the crane load? You could see you apply the crane vertical load without moment, without impact. You apply the crane vertical load without impact. So the scenario where there is no impact on the structure during crane application. Then you apply crane wheel loads considering impact. So look at the two scenarios. You consider when there is impact during rigging. Maybe the operations person, mistakenly does not provide guidance to the crane operator, and then you have that impact. And then you apply the critical crane loads which shear. So you apply the crane loads on the structure, that is on the crane girder, such that to cause a significant shear force. You also do that. And then you also apply horizontal surge load. Okay, you apply horizontal surge load. The code states your lateral loads applied through surge is 10% of the weight of crab plus the weight lifted. So once you apply this crane load, you carry out your load combination in compliance with the code of practice, and then you perform your analysis. This is how far we'll go for now. We would continue with this session in our subsequent trainings and explain to you how to interpret the results. We'll explain to you how to interpret the results. So this is typically what you would do when you intend to design a crane girder. You calculate all the crane loads, you extract information from the crane vendor, some very crucial information from the crane vendor. When you load and apply your loadings and apply the load combinations in compliance with the code requirements, you would have serviceability limit state combinations. You have crane load combinations with dead loads. You have crane load combinations with imposed loads. You have crane load combinations with lateral loads. Okay, the code specify how the crane load combinations will be applied. You would have to follow that strictly. You see very clearly there are combinations that will cater for the crane loads without impact, crane loads with impact, crane loads without lateral horizontal force, crane loads with lateral horizontal force. You would make all these combinations clearly As soon as you do that, you run your analysis and then you go to your processor. Once you go to your processor, you select all the critical combinations at serviceability and ultimate limit states, and then we check the member utilization ratios. Okay, as you see, only one structural member in this case approaches its critical stress ratio. So just this member, and the actual ratio is just 1.025. And this is where you have, look carefully, this is this member that's carrying the crane girder. So we can carry out member strengthening on this structural member because its existing structure has been constructed. You can carry out member strengthening, check where the maximum moment is, and then carry out member strengthening and redesign and ensure that the structure is satisfactory. Thank you very much. Always continue to like this page. Be rest assured that we will provide continuous responses to your questions and solutions to any structure related problem. Thank you.